Good evening. This is Fahim Faisal, and today's class is about MOSFET characteristics and applications. The name MOSFET stands for metal oxide field effect transistor. To know more about MOSFET, first we need to know what is a transistor. Well, a transistor is a three-terminal semiconductor device where the voltage and current of one terminal controls the electrical behavior of other terminals. It is capable of current, voltage, and signal gain. In this figure, a bipolar junction transistor is shown, which has three terminals. They are emitter, base, and collector. MOSFETs are the most basic type of field effect transistor. The name field effect transistor comes so that the electric field of the controlling terminal controls the basic transistor action. It is used in switching and amplifying signal, and it is a voltage control device. That means the voltage of controlling terminal controls the electrical characteristics of the other two terminals. As it is shown in the figure, the basic MOSFET symbol, it has three terminals. They are source, gate, and drain. The gate terminal is our control terminal. The MOSFETs can be divided into two types, depletion mode and enhancement mode. Depletion mode device is normally on and enhancement mode device is normally off. That means we need to put a positive voltage to turn on the enhancement mode MOSFETs. And depending on the channel types, it can be further divided into two types. There are P channel and N channel. The N-channel enhancement mode MOSFETs are the most common type of MOSFETs. Therefore, we will now talk about this. As it is shown in the cross section, the P-type substrate provides the physical support of the device. And we can see there are two heavily doped terminals that acts as source and drain, and a thin layer of oxide is deposited above the surface. And finally, a metal is deposited above the oxide, which constitutes our gate terminal. As we can see, they are basically two back-to-back PN junction. The current enters the drain and leaves the source, as if the source is the source of current and the drain terminal drains the current, hence the names. Well, as I have mentioned earlier, the gate terminal is our controlling terminal. So in the basic operation, at first we'll analyze what happens when there are no gate voltage. We can see the device basically acts like two back-to-back diodes. Therefore, no matter how much voltage we put on drain or source terminal, there will be zero current always. Now we increase the gate voltage somewhat, and it is still less than threshold voltage. The threshold voltage is defined as the voltage needed to turn on this MOSFET. And in this case, there is no electron inversion layer created, and the drain to substrate PN junction is still reverse bias, and therefore there are zero drain current. Finally, when the gate voltage is sufficient enough, in other words, it is increased and it crosses the threshold voltage, finally the voltage is sufficient to create a layer of electrons, which is called the inversion layer. The electric field from gate terminal accumulates the negative charges under the terminal. Now, as small drain to source voltage VDS is applied, electrons can now flow from the source terminal to the positive drain terminal. Therefore, we can control the current flow of the two terminals by controlling the voltage of the gate terminals. The thickness of the channel indicates the relative charge density, which is uniform for small VDS. This will be crucial in explaining the IV characteristics of the device, and the IV characteristics is one of the most important characteristics of a device. So in this case, we assume that VGS, or the gate voltage, is greater than the threshold voltage. In other words, the MOSFET is on. First, when small amount of VDS is applied in this region, the current increases as we increase the VDS. Next, when the VDS value increases, the drain voltage increases and the voltage drop across the oxide near the drain terminal also decreases, which means that the induced inversion layer charge density in this channel also decreases. Therefore, the slope of the IV curve also diminishes. When the VDS increases to the point the potential drop across the oxide at drain terminal is equal to VT, the induced inversion charge density is 0 at drain terminal. This effect is schematically shown in this figure. As we can see, at this point the incremental conductance at drain is 0, which means the slope of ID versus VDS curve is 0. When VDS becomes larger than the saturation value, VDS sat, the point in the channel at which the inversion charge is just 0 moves towards the source, as we can see in this figure. In this case, the electron entered the channel at the source and traveled through the channel toward the drain. And then at the point where the charge goes to 0, the electrons are injected into space charge region and this electric field sweeps the electron away. Therefore, the current remains the same and we can say this is the saturation region of MOSFET because the current is saturated. So this is the basic ID VDS curve. We can see it is divided into two regions. They are non-saturation or triad region and saturation region where current is saturated. There is another region where the MOSFET is said to be in cutoff. In other words, the MOSFET is off. And these are the equations that governs these MOSFET regions. Well, why MOSFET is important? Well, MOSFET is one of the most important devices that has been ever invented. MOSFET requires small area on the chip compared to the BJTs. They can be used to realize various digital and analog functions. Then their operation requires little power and manufacturing process is very simple. The whole VLSI industry depends on MOSFETs as the properties of device made it possible to pack a large number of transistors in a small area. There are various applications of MOSFET. It is used in digital integrated circuits, calculators. It is used in memories and CMOS logic gates, used in amplifiers and in various RF frequency circuits. And this is possible due to the very high speed of MOS transistor. As the channel length gets reduced, the speed also increases. Thank you. Any questions are appreciated. This is Fahim Faisal. I am concluding my presentation now.